Alright, grade 12s, we're now going to look at the table of standard reduction potentials. You must know how to use this. Please, if you haven't got it out already, pause the video. Make sure you've got the little booklet I gave you at the beginning of the year, which has the Redox tables on, because it's very, very important. Number one, we use table 4B. You will always be given two tables, 4A and 4B. You can use either, but the way I'm going to show you to understand the table requires you to know 4B. What you need to do when you get into your exam, you walk in, you cross out table 4A and you ignore it. Okay, so you've got to make sure you get used to that. You will be given both. The table is set up so it gives a list of oxidizing agents and reducing agents. Okay, the oxidizing agents are the first elements mentioned as the reactants as written on the table. They're all reduction half reactions, okay? But the oxidizing agents are the elements that are given as the first element on the table. Those are your oxidizing agents. The ones at the top, very weak, and there will be an arrow that says that this is the increasing oxidizing agent ability, okay? At the bottom, F2 is your strongest oxidizing agent. The reducing agents are the first product given. Okay, that then is your reducing agent, right? So, lithium is a very strong reducing agent. Fluorine minus is a very weak reducing agent, and there'll be an arrow that means it goes up like this. Okay, being able to identify these are actually quite important, because when we write the reaction, we always write our reaction so the top part, is written as an oxidation half reaction. So when we want an oxidation reaction, it's always written from right to left, because I want substance giving away electrons. The reduction half reaction is always written right to left. Okay, but when we're doing this, let's just get rid of all of this. We need to recognize, alright, that lithium would be one of my reactants and fluorine would be one of my reactants. When I join them together, if you look carefully, you've got a Z. When I'm doing a reaction, I would go lithium becomes lithium plus one electron. I now write it as a single arrow. I don't worry about the double arrow anymore. Okay, if you write a double arrow here, you get naught. The fluorine gets added to 2 electrons and it becomes 2F minus. Okay, it's now the reduction half reaction. For a galvanic cell, the oxidation half reaction is always at the top. Always, always, always. Alright, so this is the oxidation reaction, which also makes this the anode. That's the reduction reaction, so that makes this the cathode. So when I'm doing a calculation, there's the anode value that I'm going to use. There's the cathode value I'm going to use. Alright, let's do an example. Always best to look at it as an example. And I've already told you that. So, consider a silver magnesium galvanic cell. So they're telling me it's a galvanic cell. They're not telling me which is the silver, and they're not telling me which is they're not telling me which is the anode, and they're not telling me which one is the cathode. I need to find that out. So, I look on my redox table and I go, okay, let's find the magnesium or the silver, but there's the magnesium, minus 2,36. We're also using silver. Silver's over here. Ag plus goes to Ag. Okay, now if you look carefully, I'm going to go here. There's the magnesium. There's the silver. So this can be written like a Z. What does that mean for me? It means that the magnesium will go to magnesium 2 plus 2 electrons. So in other words, it's oxidized, so it's the anode. The silver will be Ag plus 1 electron, which goes to Ag. It's reduced, which makes it the cathode. Well, now we can go look at the rest of the questions. Okay, make sure you've got your table in front of you, because it'll make more sense now. So, they want us to predict the half reaction. Well, we just did that. Magnesium goes to magnesium 2 plus 2 electrons. Was the oxidation half reaction. Predict the reduction half reaction. Well, if magnesium's reduced, sorry, is oxidized, silver must be reduced. Ag plus plus 1 electron goes to Ag. All right. Which electrode is the anode? It's the one where oxidation takes place. It's the magnesium. Which reaction is the cathode? It's the one where reduction takes place. That's the silver. Done. And then they want the cell notation. You have done this so much in this section. All right. So anode, magnesium gets oxidized. Cathode, silver gets reduced. All right. Nice and simple. Nothing really difficult here. Okay. Let's look at the next one. Now they say to calculate the EMF of the following cells. And its first one is a zinc copper cell. Okay. Here it's about finding the zinc and the copper in the table. So let's go to the table. Let's take out what I had last time. Okay, it starts to get a bit messy. Alrighty, so zinc is there. Now if we look here, we have a copper reaction, a copper reaction, and a copper reaction. First thing you need to take note of, this copper reaction you're never going to use, because it's Cu2 plus going to Cu plus, both of which are ions. Okay, never going to happen. You can't use it here. This one requires you to use copper with the copper 1 plus charge. They have to tell you you're using copper 1. If they don't tell you it's copper 1, you're never going to use it. So that means I need to use that equation where I have plus 0.34. So zinc's at the top, copper's at the bottom. That makes zinc the anode. That makes copper the cathode. I just now need to put these values into the equation. We've done the hard work. And we get 1,10 volts. These are all galvanic cells, okay, unless they tell you otherwise, which means E cell must be greater than 0. It must. Okay? If it's not greater than 0, then it's wrong. It's as simple as that. Okay? Very simple. Now they want copper aluminium. The nice thing here is we've already found the copper, right? So we don't need to worry about that. I'm going to take that out. We know that we're using the copper. Now I need aluminium. Oh, wait. Aluminium's just a little above where the zinc was. So aluminium, which is the anode, is minus 1,66. Copper is the cathode, so it's plus 0.34. We can put that into the equation. Oh, look, and once again, positive value. We are very, 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 very happy. Okay, we good? Now we have aluminium lead. Okay, so we've already found the aluminium. We need to now know where the lead is. So let's get rid of the copper. We don't need that one anymore. And over here, oh wait, there's the lead. It's below the aluminium, so the aluminium is still the anode. The lead now is your cathode. Okay, we put it into our equation. We're all very, very happy, and we get a positive value. So of course this is nice and easy, right? There's nothing, whoopsie, sorry about that. So there's nothing difficult about that. The hard thing is to be able to find out where the anode and the cathode is. That is all about knowing which is at the top and which is at the bottom. Okay, we're all happy. Now the next question was to write down the cell notation. I really suggest you try to do this on your own first. So pause the video here and you can see the reactions, or you can just pause it, go back, whatever. Please, you really need to do the activities on page 368 and 369. The memo is in Teams. Okay? One last little section we need to do. And that's the relationship between current and potential to the rate of an equilibrium. The current measured in a circuit, and as well as the potential difference, is directly related to the rate of reaction as well as the degree of chemical equilibrium. Chemical equilibrium, it's quite a complicated equilibrium, so we don't need to stress too much about the reactions that happen, but there is an equilibrium that's going to be formed. A galvanic cell works on the fact that there's a difference in energy between the anode and the cathode. That difference in energy causes the electrons to move from one side to the other. Once we get to a point where it's reached equilibrium, for example, When it reaches that equilibrium, it's reached this place where it's reached a zen, okay, it's the best way to think about it, and it goes, okay, no more difference in energy in each cell, that's fine, I'm going to stop working. Okay, so the potential difference of an electrochemical cell decreases with continuous use. You all know this, you've all used batteries, and so does the amount of current. They're related to each other. The current is at a maximum when the potential is at a maximum. It's fairly straightforward. Now, how does a cell go flat? It's not because the chemicals get used up. Okay. When the reaction starts, the forward reaction rate is very, very fast. You know this from rates of reaction in equilibrium. So the forward reaction rate has to start to decrease and the reverse reaction rate will increase because it needs to try to get to an equilibrium. As the forward reaction decreases, the rate of the transfer of electrons also decreases, so the E potential gets 0. Goes smaller and smaller and smaller. This decrease will decrease the E cell. Straightforward, nothing difficult. As the cell potential decreases, so does the current. They go together. Alright? Eventually, both rates, forward and back, will equal each other. So now we get to the state of a dynamic equilibrium. As a result, no electrons will be transferred because they are very happy, because we have a situation where oxidation happens at the same rate as reduction happens. One is forward, one is reverse, and vice versa, all the rest. We've reached equilibrium. Everyone's happy. When that happens, no current will flow. Whoopsie. And the cell is flat. So when does the cell become flat? When it reaches equilibrium. Okay, that's the pointer. And with that, we are finished with electrochemistry.